let's say you've got a triangle shaped like this. Let's make this be the line y equals x over 2. And oh, for good measure, let's go out to x equals 4 here. And this would be y equals 2 right there. And the triangle is going to be this region right here. Pretend this is a thin plate, a thin sheet of whatever, metal, wood, whatever you want to call it, that's got a certain density function, area density. Effectively, we're treating it like a two-dimensional object, and its density varies with x and y. Don't worry about anything too practical, like how you make such things. How do you actually manufacture these? Are they really that useful? Okay. I will tell you, thinking along these lines is useful in a class like, for example, mechanics. In mechanics, you will have problems where you have to think about this kind of thing. Just make something up. I'll keep it a fairly simple function, say 3x plus 5y. What do I want to know? I want to know the mass and the center of mass. Focus on the mass first. How do you think about it? In Calc 1, or Calc 2, I should say, your density function often varies only depending on x or y, and you slice the object into thin strips, either with thin vertical slices at effectively constant values of x, or thin horizontal slices at effectively constant values of y. But here our density function varies with both x and y. And by the way, its units would be in units of mass per unit of area. It varies with both x and y, and so I have to slice it not into tiny thin strips, either vertical or horizontal, but tiny rectangles, you might say, where both x and y are effectively constant, if these rectangles are so tiny. Call the width of that rectangle. If I want to go ahead and I could, there's two notations I could use. I could use delta x and delta y for the width and height of the rectangles. When you use the delta notation, you effectively think of them as small, but certainly real number lengths. Or you could use the differential notation, dx and dy, and think of them as infinitesimal lengths, smaller than any number you can imagine. But wait a minute, I drew it to not look smaller than anything you could imagine, right? You could literally measure that rectangle. You got to use your imagination. Okay, it's all in your imagination with a goal of just gaining intuition, thinking about things intuitively, and deriving formulas. Formulas involving integrals that you can then hopefully do. Intuitively, you would think of the mass of this thing, the small mass of that little tiny chunk there, as being the mass density at that point. Effectively, that chunk is at coordinates x and y, times the small area of the chunk. This would be in grams per square centimeter, and this would be a tiny area in square centimeters, giving you a mass in grams. But then that area could be broken down into the product of two lengths, either dx dy or dy dx. The total mass of the thin plate, often called a lamina, what a beautiful word, mass of the lamina, is found by adding up the little tiny infinitesimal masses, where the integral sign represents the adding up. And use a double integral since it's a two-dimensional region with a two-dimensional density function. R is the region itself. Okay, it's a region. It's not a rectangle. It's a triangle, but R stands for region. You add up the little masses. You could write double integral of dm, effectively meaning add up the tiny masses to get the total mass. That's how you want to conceptualize that. But then dm is the density function, dA. And then when you actually do the integral, you do it either this way or that way, depending on how you want to think about the region, as vertically simple between the graphs of two functions of x, or horizontally simple between the graphs of two functions of y. And either way is okay. If we think of it as vertically simple, the region between two functions of x, then the order is dy dx. The way I kind of remember that is I remember it's sort of the opposite of what I would expect. Is sort of my initial remembrance. So the function is 3x plus 5y. I'm going to do it. It's a y there. I'm going to do it dy dx. The outer limits of integration are for x, they have to be constants. X goes from 0 to 4. The inner limits of integration are for y. Y goes between two functions of x. For any given value of x, like right here, y goes between two values that depend on x, functions of x over 2 and 2. That's if you think of the region as what's called vertically simple. If we think of the region as what's called horizontally simple, y is the outer integral. It goes from 0 to 2. And for any given y, you go between two functions of y. X goes between two functions of y, 0 and 2y. So you could also do this as the integral from 0 to 2 of the integral from 0 to 2y of the same function, 3x plus 5y, but then dx dy. I think we'll have Mathematica do all our integral calculations today. On your homework, you should still show work, unless told otherwise. But this is going to give the total mass. Let's guess the answer before we actually compute it. How do you guess the answer? Think about it intuitively. Think about trying to guess the average density over this triangle here. This function is minimized over this closed and bounded region at the lower left corner, the origin, when x and y are both 0, the density is 0 there. Effectively, you know, the molecules are not very close together near that corner, right? You could very easily break it off. And it's most dense in the top right corner where x and y are largest. Delta of 4 comma 2 would be 3 times 4 is 12 plus 5 times 2, 12 plus 10 is 22 grams per square centimeter in that top right corner. The molecules are all closer together. On average then, well, the average of 22 and 0 is 11. Does that mean the average value of this function is 11? Not necessarily, because the region's a triangle. It's hard to say for sure if it truly is 11, but it shouldn't be maybe too far from 11. Maybe if it were like an isosceles triangle like this, maybe by symmetry, you could say the average was 11. Because probably the level curves of this thing are like perpendicular to that line, is my guess. Well, not necessarily. Never mind. Not necessarily. But the fact that it's more over here than over there, you know, it's going to perhaps tend to make the center of mass more over this way. As far as the average mass goes, maybe closer to the value of this function right in this region here, where x is small, close to, I don't know, 1, and y is close to 2. I don't know. That's still close to 11. Somewhere in the ballpark of 11 is the average density of this thing. If you took that average density times the area of the triangle, you get the mass. Area of a triangle is 1/2 base times height. The base is 4, the height's 2, the area is 4. Should expect a mass of somewhere in the ballpark of 11 times 4, 44. Not necessarily exactly 44. Integral from 0 to 4. of the integral of x from x over 2 to 2. I almost said times there. It's not times, it's of. You got an inner integral and an outer one. It's almost like function composition, and like an inner function that's found by integration, and then you plug that into the outer function and do another integral. 128 over 3. Okay, 42.7. The average is actually a little less than 11. I was guessing the average from the picture was close to 11. If you wanted to find the average value exactly, you take this integral and divide by the area of the triangle. The area of the triangle was 4. The average value is more like 10.7 instead of 11. But for good measure, double check that the other integral gives you the same thing. Even if you're not asked to do this, it's probably a good idea just to confirm that you get the same answer and that you set up the other integral correctly, because it's really in the setting up that you've got the most important skill you're trying to gain out of this, is setting up these integrals, not doing them. So there's the mass. What about the center of mass? This would be in grams, 42.7 grams. The formula is written as giving you the coordinates of the center of mass, x bar comma y bar, where each of those numbers is found as a ratio, where the bottom of the ratio is the mass in both cases, m is the mass, and the top is labeled in kind of a funny way. For x bar, it's labeled m sub y, and for y bar, it's labeled m sub x. There's a good reason for that. My is called the moment with respect to the y-axis. Moment with respect to the y-axis. And why is the subscript y, and why is it with respect to the y-axis if it gives you the x coordinate of the center of mass? It's measuring, in a vague way, the tendency of the lamina to rotate about the y-axis, which is related to weighted averages of masses of small regions perpendicular to the y-axis in the x direction. The formula for this is the double integral over the region of x times the density function. Where does this come from? I'll let you read the details if you're interested. It comes from effectively the law of the lever. The fact that if you've got two masses on a teeter-totter, if you want the teeter-totter to balance, the mass times the distance should be the same on both sides. Or effectively, if you multiply the mass times the position of each object, where there's a positive position to the right of the fulcrum and a negative position to the left of the fulcrum, and add those up, you get 0 for the teeter-totter to balance. If you take that idea and generalize to thinking about infinitesimal chunks of thin plates in horizontal or vertical directions, that's effectively where the moment formula comes from. The moment with respect to the y-axis, or with respect to the x-axis, is the numerator for the second coordinate, the y coordinate of the center of mass. The integral formula involves y times the density. It's with respect to the x-axis horizontal, but it's based on a distance perpendicular to that in the y direction. That's why you integrate with respect to, with this extra y factor in there. But it's measuring the tendency to rotate around the horizontal x-axis based on, again, weighted averages of masses times distances effectively in the y direction. Okay? As far as figuring out what these things are, again, you should be able to do it by hand. For our purposes, we just have Mathematica do it. So for m sub y, you need an extra factor of x in here. The moment there for m sub y, that's going to lead to x bar, center of mass in the x direction is going to be 72. X bar itself will then be 72 divided by 42.6667, about 1.7. Close to 1.7 is the x coordinate of the center of mass. 2 is about here, 1.7 be around there. It's not too far, probably, from this little box that I made. In the y direction, probably the answer is going to be between 1 and 2 as well. Multiplied by y, then you're calling this quantity actually m sub x, vertical distance away from the x-axis, to measure the tendency to rotate around the x-axis. Okay, so that's mx. And then y bar is 64 divided by 42.6667. Yes, still between 1 and 2, in fact, 1.5. No guarantee that was going to turn out so nice. But once again, you can do the integrals either dy dx or dx dy, and you should get the same answer.